something about my work with Jennifer and Denise on the generalization of hand localization shifts in motor adaptation. Knowing where your hand is, localizing your hand, is important for movement and for adapting movements. So it is interesting for us to understand how we do this, how we localize our hand. Okay, and this can be based on signals from the motor system, predicted sensory consequences which get updated, and it could be based on sensory signals, proprioception, that gets changed in motor adaptation as well. So how do these two get combined? We've tried some other approaches before, but here we're going to look at generalization curves. We're using a visuomotor adaptation task where we gradually increase the rotation to 50 degrees in steps of 10 degrees. And this means that both these motor and sensory changes are gradually increased, and we can see what happens to the generalization curve throughout this experiment. So after every training trial, where we use a single target, which is different for participants, but every participant has one training target, people either do a no-cursor trial, which is supposed to measure the motor changes, and we do a hand localization trial, which may depend on several signals. For both of these test trials, we use the same 8 locations so we can compare the generalization curves. All right. Okay, let me minimize the webcam so you can see the graph. I'm going to be showing 2 of these graphs, one for the no cursor reaching and one for the hand localization. You'll see on the x-axis in the middle is the train target. This is where people have to move their cursor, and then on these tick marks here, this is where they actually have to move their hand. Alright, and then on the y-axis is the change in the measurements relative to the 0 degree condition. Okay, and we can see in the no cursor reaches that there is here a peak at the train target, so the movement that you're training with elicits the largest change in movements, to no one's surprise. And we can see that this stays the same for all of the 5 rotations. Okay, so we can move on to the hand localization, the more interesting one. It's the same graph except for the y-axis. The scale is a little bit lower because these changes are usually smaller. Okay, we can see for 10 degrees there is not really a peak. You see that the confidence interval spans the whole range where I allow the peaks to be. However, for 20 degrees you do see a clear peak, which is located around the train target as well, just as above. But for 30, 40 and 50 degrees, this generally shifts over towards where the hand actually was during training. However, it doesn't shift all the way. If it would shift all the way, then these medians here would lie on this gray diagonal line. They don't. They lie on this line, which indicates about 32% of hand localization peak shift relative to the actual shift in hand location. So this is not the height of the curve, but the shift of the peak that I'm talking about. And this indicates some mix of signals. So you could say it could be that where the sensory changes are somewhere in between the visual feedback and the proprioceptive feedback. So the visual feedback, where the cursor goes, should be at this train target, whereas the proprioceptive feedback moves with the hand. It could also be, so these are constraints on the sensory changes. It could also be that when we localize our hand, we do mix some of the motor and sensory changes and combine them, and so the motor changes, as we saw in the graph above, peak at the train's target, but the sensory changes might not. Either way, there's some mix of signals, and we want to disentangle this further. And I would love to have your feedback on how we could do this, or where we could take this further, like what other interpretations there are for this data. All right, thanks very much. Hope to talk to you soon.